This is Carlos Coe's Transport 1 Homework 4, and we're going to be solving for the fluid height and flow rate of a two-sphere system that are connected by one tube, and there's an outlet tube and there's an inlet. They're open to the top and there's an inlet. So first we need to import what we need. So from SciPy integrate import solve IVP enter import jax.numpy as pio no it's JNP, and we're going to use jax to make the calculations easier. It's good for calculating. Import jax. My enter button is being iffy. From plots, and we're going to do this so we can see our results. And we're going to import the plotly graph objects as Go. This will allow us to not having to keep type graph object. And then we import the plotly.io as pio, and this will help change the graph, how the graph looks. And we want to make the pio template equals plotly dark. And this will change how it looks, so put on a dark background and make it easier to see. And then we want to import math, so we can use pi. Templates default. Oh gosh. That's an abomination. Sub. Oh my gosh, I'm bad at this. Alright. So those are all the tools we need. And now we want to set it up so it runs to 200 seconds. We want to evaluate at 100 and 200 seconds, so it runs to 200 seconds. 10 equals 200 TQ 2 G is equal to JNP dot square root 2 times 9.81, and this allows us to solve for the this square root that we're going to see a lot in the problem, and it makes it so we don't have to keep going back and do it. It'll do it for us, which is a great thing. And then we want to put in our dimensions. So the first radius is 4. Second radius is 2. And then both of the areas of both the pipes are both 0.2. So A12, the pipe going from 1 to 2, 0.2. A2 equals 0.2. And then the initial heights is 5 and 3 for the initial liquids in each sphere. H1I equals 5. H2I equals 3. And then we want to insert the cross-sectional area equation that we found in the last video using the Pythagorean theorem. So we have AC1I equals math, so pi times R1 squared minus H1I minus R1 squared AC2I equal to pi times R2 squared minus H2I minus R2 squared. Alright, so I'm going to make sure that's all good. And then we want to input the equations for the flow rates that we found in the last video. So Q12I equals A12 times JMP dot sine. So sine times H1I minus H2I times SQ2G times JMP dot square root the absolute value of the first height minus the second height. And then for the second one, Q2I equals A2. This is much simpler. SQ2G times JP dot square root of H2I. And our Q1 initial is equal to our Q12 initial, so the in into the first one is equal to the in, the out of the first one initially. Q12 I and I. I'm just gonna make that I. And then Q2 I and I is equal to Q2I, the initial flow rate of the second, minus what's going into it from first, obviously. And then we can display these here just to kind of see what we have. So we'll say print F Q1 I and I equals bracket Q1 I and I bracket. Oops. That will give us back the values that we have, and there's an error. Of course. SQ2G not defined, but I did define it. I don't know why I did that. Okay, and then we can see there are the values. So then we want to show that at this and this. So we want to show that there's multiple variables, so at any given point of the time we can have two different v's, and we show this by say define this as define switch t v1, so we can have it at different values of v at the different times. v1, v2, t switch scale. We return. We use the jacks, and then. And now we want to do the evaluating, so we'll input what we want to be defined as the inlet flow rates. At any given time. We're going to use a return switch function. Just because it can't change, all these things can change. Switch T, and and we times this by 0.08 because that is the coefficient of this efficiency times Q Q1. And we want to run it to 100 seconds, and the scale will be 1. So we'll switch to 100. Do the same thing here for 2. And the coefficient here is 250%, so we times it by 2.5 times Q2 and scale of 1. Of course, I believe this is supposed to be 1. And we're going to plug this in. What? Oh, 0.8 times. Okay. So now what we do is we're going to bring in our Jax function again. So in order to plug everything in, so at Jax jits we're going to define the change of height over the change in time. So then we show that showing the T and H H1 is equal to, is actually equal to H0, H2 is equal to H1. And then we're going to show our functions that we had for Q12 and Q2. I keep doing that. And we'll take the eyes out. Okay. So now to turn this this will be, this will just be our function really. So it'll be Q1, this minus this, this minus this, and then they're all over their respective cross-sectional volume, cross-sectional areas, circles. So Q1 in of T minus Q12 that's simpler for us. Q12 divided by AC1, no? And then we have Q2IN of T plus Q12 minus Q2 AC2. Oh, shoot. What? Hey, give me a minute. Nuh-uh. Some came in the mail for you today. That should work now. Okay, good. So now we're going to solve for the change in height over the change in time from the equation that we got in the previous video. So we'll do res solve IVP dH dt 0, 10, and 200. It's what the scale is going to. H1 I H2 I method equals redow. Dense JMP 10, and we go to 201 because we want to count as a 0. We go to 0 as second, so 201 points, and then solution equals res dot solution t plot. Give me like 10 minutes. Jacks.